In the first part about variables, we saw how numeric variables work. In the second part, I'll explain how alphanumeric variables or text variables, which is the same thing, work. In Sinclair Basic, we differentiate variables type using the dollar $suffix. This is not longer necessary and is ignored, as it is enough to define them with dim as a string. Each character or letter in alphanumeric variable occupies 1 byte. In addition to that byte, we must add 2 bytes at the beginning of the string to indicate its length, plus another 2 bytes that store the memory addresses where the string begins. In other words, an alphanumeric variable containing the text hello123 occupies 8 bytes, one for each character, plus 2 bytes to store the string length, and another 2 bytes used internally to store the address where the string begins, for a total of 12 bytes. This means that the string hello123 is stored in memory as in hexadecimal format 0800486566C6C6F 313233. The first 2 bytes indicates that the string contains 8 characters and the remaining bytes represents each character in order. For advanced users of those coming from the C language, strings in Boriel Basic are not terminated with a zero. Alphanumeric variables can store letters, numbers, symbols, basic tokens, UDGs, and even control codes. This table, containing the spectrum character codes, is very useful and worth keeping handy. In the column headers, we can see the first hexadecimal digit of each character, while the row headers contains the second digit. Together, they form a hexadecimal number that determines the character code, that is, the value stored in memory. For example, the uppercase letter A is located at column 4 and row 1, so its ASCII value is 41 in hexadecimal. Unlike numeric variables, there is only one type of alphanumeric variable, since these variables can automatically grow and shrink without requiring much attention from us. Another important detail is that they only support the addition operation, which simply concatenates two variables one after the other. For example, if variable A contains the string hello and variable B contains even, and we also add the string 123, the resulting string will contain hello even 123. However, even though we cannot perform arithmetic operations other than addition, that does not mean we cannot manipulate strings however we like. For example, the program strtest1 prints test one chapter at a time, thanks to the use of parentheses. First, we clear the screen with CLS. Then we call the printTest subroutine, which the coordinates where we want to print the test itself, and the printing delay. The printTest subroutine accesses the following parameters: I for the row with the test will be printed, X for the column, text for the text to print, and delay for the pause between characters, measured in units of 20 milliseconds. We declare the variable n, which will be used as a counter, and position the print cursor at coordinates e, x. We define a for loop that goes from 0 to the length of the string. The length function returns the length of a string in characters. Now we print the character located at position n in the string. By using parentheses, we indicate that we want to retrieve only a single character, specifically the character at position n. We print that character with a semicolon at the end, so that the cursor remains in place and does not move to the next line. We emit a short sound and pause for the amount of time specified by delay. Try printing using different values for delay, such 1 or 10. We can retrieve not only a single character from a string, but also a range using 2, as shown in the example strtest2. In this example, we start by cleaning the screen and calling the print_scroll subroutine. The print_scroll subroutine accepts the parameter I to indicate the row where the text will be printed, the text itself, and the delay in units of 20 milliseconds. Print_scroll uses three local variables: n, which defines the position of the first character of the string to be printed; f, which defines the position of the last character to print; and l, which stores the length of the string, avoiding repeated calls to len, since reading the value of l is faster than calculating the string length each time. We add 32 blank spaces at the beginning of the string and 1 space at the end. This causes the text to enter from the right side of the screen and disappear clearly when finishes. Without the 32 leading spaces, the text would start from the left side, which is not visually appealing and would also create a jump when the scroll restarts. Likewise, without the trailing space, the final character of the text will not be erased, leaving an unwanted artifact on the screen. Next, we prepare the variable so that n starts from the first character of the text, and l stores the length of the text obtained through len. -1, since string position starts at 0, unless we instruct the compiler otherwise. Now we start a while-when loop that will continue until a key is preset. The first thing we do inside the loop is define the last character to print, which is the first character n plus 31, the width of the screen. If the end position exceeds the length of the text, we will print only up to the end of the string. Then we print on row I the position of text that goes from position n to position f. We wait for the amount of time specified by delay and then move to increment the start of the string, which is defined by variable n. If n is equal to the total length, we reset n to the beginning of the string, that is, to 0, creating a continuous scrolling effect. Otherwise, if we have not yet reached the end of the string, we increment n by 1. The string.bash library provides a number of functions that are not implemented in Sinclair Basic, but are available on the other computers of the same era. These functions include mid, which returns a portion of a string; left, which returns the beginning of the string; right, which returns the end of the string; strpost and strpost2, which return the position of one string within another. For example, house is contained within the word greenhouse. On the other hand, in str returns 1 if a string is contained within another string, or 0 otherwise. UCase and UCase2 convert a string to uppercase, while LCase and LCase2 convert it to lowercase. LTrim, RTrim, and trim remove characters, usually space, from the beginning to the end or both sides of a string. Meanwhile, isDigit returns 1 if the first character is a number, and isLetter does the same if the first character is a letter. With this library, we could build a parser for keyword entered commands, justified on screen, and many other useful things. And that's everything I wanted to tell you about variables. Although I leave the topic of arrays for another chapter.